So hello, welcome to another day of class. Today we are going to finish chapter 10. It shall be a musical ending of chapter, mostly because I right now have a whole bunch of sound making things right here. We'll get into that. Yeah, we've been talking about springs. And then after talking about springs for a while, we're like, oh cool, they bounce up and down. We're good with that. And then we started talking about pendulums. And we actually left off mid talking about pendulums. I said that the period of any pendulum is given by 2 pi square root of L over G, where L is the length of the pendulum. That right there is the last slide we covered. So let's jump in with a practice problem. So we're going to do a problem about a clock. This clock is one that is directly beneath me right now, actually. This is a clock that I own. It's in my wife's office downstairs. And what you can see is in the middle of the clock, there's, sorry, I like how the fact my cat keeps coming through since it's on loop. The pendulum is actually kind of how it tells time. It's how it keeps track of time. What it is it marks 1 second every time the pendulum passes through the middle. So my question is, how long is the pendulum? Assuming it's a simple pendulum. Now, let's talk about what I told you. I said it's 1 second every time it passes through the middle. So let's look at the pendulum, right? When it goes jink, jink. One period is from heel to heel. And we can look at how many times it passes through the middle in a period. It goes once going to the right and once going to the left. Well, that's probably your left and your right. That's backwards. So once going to the left, once going to the right. That each period passes through the middle twice. What that means is that the period of the motion must be 2 seconds. So I'm going to say the period of motion of this pendulum is 2 seconds. Which one Mississippi 2? Yeah, it's pretty close. 1 Mississippi, 2 Mississippi. It's pretty close. The GIF might have changed the speed. There's a whole bunch of things I can get into in that. What is its length? Well, if I want to find the length, the period of any pendulum is 2 pi square root of L over G. I'll just solve this for length. How I would solve this for length is I would first divide both sides by 2 pi, getting the square root alone on the other side. Once I do this, what I can do is I can square both sides. But when I square both sides, that'll get rid of this square root. And when I square both sides, I have to square everything on the left. T becomes t squared. 2 becomes 2 squared, which is 4. Pi becomes pi squared. And if I multiply both sides by g, I can get an equation for the length. That the length is going to be g times t squared over 4 pi squared. And you get that the length of the pendulum is just shy of a meter. Now, I'm going to be honest, that's not exactly correct for that clock. That's because there's also a lot of gears and shit going on that's kind of affecting it and changing it from being that simple. But if it was a simple pendulum, it would have to be about a meter long. Questions? Okay. Other things with pendulums and springs. For springs, we gave a series of equations for position, velocity, and acceleration as a function of time. We can actually do that for a pendulum also. See, for a spring, we said its position was its amplitude cosine omega t. For a pendulum, we'll just say its angle will be the angle, the maximum angle, cosine omega t. Except I'm in a logical world. When dealing with a pendulum, I should probably do everything in rotational terms because, right, it's moving on part of a circle. I'm not going to do that mostly because then omega would mean two different things in the same equation, which gets messy. But I can define the amplitude as how far away we are. Sorry, I want to italicize that S. As how far away we are from the equilibrium point. That this is the point, how far over we are. Like, how far is this distance right here? That'll be the arc length S, where S will just be L times theta. So I can find how far away it gets. And using the same logic we did for a spring, we can find the velocity as a function of time and the tangential acceleration as a function of time. Now I'm saying tangential because it is something moving on a circular path, so there is centripetal acceleration. Although the centripetal acceleration is stupidly complicated since the velocity is changing as a function of time. Any questions? Okay, so that period equation, T equals 2 pi squared of L over G, that is assuming a ideal pendulum. It is assuming a heavy weight on the end of a string that weighs nothing. And this string here doesn't weigh much, but it doesn't weigh nothing either. And even when you go, I did actually save that, open all my videos because I don't need that video, I thought. Even if you have like those that, oh, it was just like a ball on a string. Or if I do like this bowling ball on a string from this problem. I mean, the rope weighs practically nothing compared to the bowling ball, but it still weighs something. And I can actually put other things move in a pendulum, like a pendulum, that are even less from the ideal. If I put a hula hoop and attach one side to a nail, I can put it and it moves like a pendulum. Like that's simple harmonic motion. It's just like a pendulum. But I can't just say L over G here. That is what is called a physical pendulum. A physical pendulum is a real world pendulum, something that you deal with the mass of the string, or it has, some funky shape like this guy. And what we'll say is for a ideal pendulum, T equals 2 pi squared of L over G. For a real pendulum, instead we'll use the moment of inertia. As I notice another typo. This is what happens when I'm actually staring at this instead of it behind me while I'm lecturing. See, for a real pendulum, the period of motion would be 2 pi squared of I over mgl. And I in this equation is the moment of inertia around the pivot point. We covered moment of inertia a few chapters ago in chapter 8. But yeah, it's back here. We'll just say the moment of inertia around that pivot point. And L will be the distance from the pivot point to the center of mass. That it won't just be the length of a string. Once again, going to this, how can it be the length of the string? There is no string. And if I have no string, I can't use the length of the string. But I can say it's the distance from the pivot point to the center of mass. Where the center of mass for my hula hoop, well, that's just going to be the center of the hula hoop. Let me show you with a problem. And my problem is this. This hula hoop has a radius of a half meter. The whole thing, is it actually over here? No, I didn't bring it home. The whole thing has a diameter of about a meter. The radius is half a meter. And I put it onto a nail on one side and set it oscillating. What's the period of motion? Given the moment of inertia of a hula hoop is 2 mr squared. Now, can I make this repeat? Using a different video thing today. Sure I can, I just don't feel like finding it. If I want to do that, sorry. Hey, fuck it, I give up.
You just had it there. It was under view on the bottom. It said loop.
Ah, there you go. Yep. Thank you. I should actually read what I'm doing. So, if I want to go and find this, I need the moment of inertia of the hoop. And we know the moment of inertia of a hoop. We've covered before what it is around the center. We've never talked about the moment of inertia of a hoop around the edge, or how to solve that. It's not something I expect you to know, but I'm just going to tell you. The moment of inertia of a hoop around its center is 2 mr squared. So I can say the period is, disappeared anyways, is 2 pi square root of I over mgl. And what I would do is I can solve this, try to solve this for t. Well, I don't have to solve t, it's already rearranged actually. So I just can plug in. And what I would do is say my moment of inertia is 2 mr squared. So I'll just plug that in. This will cancel out my m's. But also I have two things here, R and L. But R is the radius of the hoop. L is the distance from the nail to the center of mass. But the center of mass of a hoop is the center. The mass is spread around that. R and L are the same. So this would be 2m all squared over mg all. And as I said before, I got m can cancel out, and all squared over all will reduce. And so the period will be 2 pi square root of 2 all over g. To which I'll plug in some numbers and solve. And you get a period of motion of 2.01 seconds, which, let's see, 1 Mississippi, 2 misses. It's close. I mean, I could probably try to get it exactly with 11. Yeah, that was about 2 seconds according to the timer in the video. Not so bad. Any questions? Okay, that's simple harmonic motion. And the way when I say things like that, it normally means I'm wrapping up, and we're only 10 minutes in today's class. So not too surprising, that's not what's happening here. But that is simple harmonic motion. That is what you need to know about simple harmonic motion. What I want to talk about for the rest of this class is a related topic, kind of, which is waves. You see, when we talked about simple harmonic motion, we put everything in those sine waves and cosine waves. And waves is a related idea. So let's talk about those in detail. A wave, what it is the motion of a disturbance. That doesn't immediately make sense, but let's take a look at, wrong thing, nope, no, this one. Let's take a look at if I have a string, right? And if I, it's behind my video. I'm like, I can't see the button I want to press. If I go and flick one end, the wave moves down. Then you can see, yep, there it goes. And how even if I said oscillating, the motion that I'm going is moving to the right. Slow it down, actually. Now, what we have here is that the spring itself is not moving down this path. The disturbance is moving down the path. Look at this green dot right here. That when this gets flicked, this green dot goes up and down, but it doesn't move to the right. What moves to the right is that hump. What it really is the transfer of energy without mass. That when it's higher, it has more potential energy, and we're traveling that increase in potential energy down the road. That is what a mechanical wave is. Now, mechanical waves need two things to exist. First, it needs some sort of disturbance. Sorry, here we go. That if I want to put a wave going down this string, nothing happens if I just hold it still. It's when I flick it, you get a wave. Same idea with water, right? That if you have a bunch of water just sitting still, it just sits still. When something drops into it, then you get the ripples. You know, the water's rippling. Now you know the dinosaur is coming to go all Jurassic Park on this. That's what you need, something to cause the disturbance. On this guy, if I don't click anything, nothing happens. It's only when I click this, the wave starts. Let's see if I can make this smaller and still fit. The other thing you need is a medium. If I just hold my two hands like this and go like that, you don't see much. If I do it like this, now you can see a wave in this string. That's only when I'm actually moving the string can you see it. But here it doesn't happen. You need it to actually be there. And they kind of need to be connected to each other, right? If I have the string here and I just start like shaking my hand beneath it and not on it, it doesn't really work. It has to be connected. Okay. Now, when we talk about waves, the easiest way to talk about waves is what is called a traveling wave. And we're going to get into some other types as we go, but let's start there. A traveling wave is what I've been doing with this guy. You get a rope, you flick one end, it moves with a set speed. That is a traveling wave. That when I flick this and make the wave move, I have one. Even if I set it going constantly, this is still a traveling wave. That we can see that these peaks are whoop, whoop, moving right down the path. Now, traveling waves themselves come in two flavors. What you've been seeing so far is called a transverse wave. A transverse wave is a traveling wave in which the disturbance is perpendicular to the motion. What I mean is the disturbance here is up and down, but the wave is moving to the right. They're perpendicular from each other. Light is one example of a traveling wave. Now, light is a weird wave. And I'm actually going to go back to this so that can be moving. Light is a transverse wave of E field and B field. Light also can move in a vacuum, which goes against the rules of what I said what a wave needs. Waves need to be in a medium. Light doesn't need it. It's weird. We're going to not talk about that. That's a physics 2 concept. But a transverse wave is when the motion is perpendicular to the movement. A longitudinal wave is when the motion and disturbance are in the same direction. Best way to see is with a slinky, which my short work is a good backdrop. It does. That if I take this and kind of push it together and move it by instead of going up and down, by going towards and away and closer and away, that would be a longitudinal wave. Sound is a longitudinal wave. It has areas of compression and areas that are stretched out, known as rarefaction. This GIF in the bottom left is how sound waves work. That is just the air molecules get pushed closer together, then spread further apart, then push closer together, then spread further apart, and it's the movement of that spread. It's kind of harder to visualize, but it's the same idea. They're both traveling waves. Just elbow this table. Now, if we're going to talk about traveling waves, we need some certain terms you need to be familiar with. One of them we've already covered, which is amplitude. Amplitude is the maximum displacement. Now, when we talked about amplitude for simple harmonic motion, it was just, how far did it go from the equilibrium? And amplitude for a wave is the same idea. It's just how far does it go from the bottom? If I start messing with the amplitude, we can have a big amplitude. Oops. Or a small amplitude. It's just going to be how physically bigger the wave is. Make sense? Amplitude is traditionally, well, I can measure a whole bunch of stuff, but here's the symbol A. There's also the wavelength. Now, wavelength is how far the wave is from one peak to another. When I say that, what I mean is that it's going to be how far from peak to peak. How far is it from here to there, traditionally measured in meters. You know what? I should use a different color because that is red. So how far from here to here? That is what wavelength is. And so you can change the wavelength. This is one wavelength. If I go and change that, now I have a very different wavelength. I doubled the wavelength here. Wavelength uses the unit. Is symbol is lambda. Looks like an upside down Y, but it's lambda. It's just the distance from peak to peak. There's also frequency. Now we talked about frequency and period earlier in this chapter. But frequency and period still have the same relationship. Frequency is cycles per second, period is seconds per cycle, and frequency is 1 over period. That isn't changing. But for a wave, when we say frequency will be, well, let's do period first. Period, which is capital T, is how long it takes the wave to go through one complete cycle. The GIF shows it, but I'll do it here. What I'll do, and let me put this back in slow motion to make my life easier, is I'll say right now, this point, oh, that is a bad color to use, blue. Right now, this wave right there is at its maximum. If I set this go, I can say as this goes, I can time how long till that P is at a maximum again. So I'll say the time from here to there, that's one period. That's what a period is. So when it goes from a spot and goes down, it returns to the exact same spot. Period, measured in seconds, symbol capital T. Frequency is just the inverse of that. That 1 divided by the period is frequency. Good so far? Now, let's look at some of these ideas. Wavelength is how big the wave is. And period is how long it takes to get there. So logically, if I take a length and divide by a time, a length divided by time is velocity. But 1 divided by period is frequency. And so there's kind of some logic you can bullshit out, but I'm just going to tell you the equation. Any traveling wave has a set velocity. How fast the wave moves, in this case, moves to the right, which is going pretty slow here. It's all in slow motion, that's why. And that velocity will just be the frequency times wavelength. That if I start changing one of these two, I just heavily changed the wavelength, made it much smaller. And what you can see is the wave itself is traveling slower. When I make the wavelength bigger, the velocity is faster. It's moving faster to the right. I'm not changing the frequency at all. I could change the frequency. That's this dial. But when I start changing the frequency, I'm getting it to go at different speeds. Notice the frequency and wavelength also changing. There's a reason for that. That gets into this tension tone. We'll get back to that. And so we can say the actual velocity of any given wave is simply wavelength times frequency. And this can be used for any type of wave. Still good? Okay. Other weird things with waves. It's going to become very important for where I'm going forward. When a wave hits a medium, it will reflect. How it reflects depends on what the medium looks like. Let's say I take this end and just make it loose. So it can move up and down. If I give this a pulse and it hits that loose end, the wave will bounce back looking exactly the same. That it comes looking like this, it comes back pointing up. That it makes no change from up to up. That'll be any time that the free end is loose, that it can move up and down. However, somehow I skipped a slide. Let's go back. However, if instead the boundary is fixed, when the wave hits the end and it bounces, it'll come back inverted. That these ends are fixed, so whenever it hits the fixed end, what was up is now down, what was down is now up. And that'll happen anytime a wave hits a fixed end, that it'll invert itself. So fixed end, you get inverted. Free end, you don't. What's also of note is that waves can interact with each other. Waves follow something called the superposition principle. When two or more traveling waves encounter each other, they pass through each other. And what actually happens at any given moment, they'll just add up what their height is at that point. Let's say you have two waves that have the same frequency, the same amplitude. I'm going to call this in phase. That wave A has a maximum at the same point wave B has a maximum. What's going to happen if I combine these two waves is I just get a bigger wave. Side note, this link right here is just to this guy. So if you want to do this on your own. That if I take a wave and I want them both loose end, this would do it. If I get a wave and have another one come the other way, they can just kind of add up as they pass through each other. In fact, you can see it on this GIF, it kind of shows it. That when two pulses come towards each other, they just add together and pass right through each other. If instead the waves are out of phase, if instead wave A has a maximum, wave B has a minimum, and vice versa, waves can actually cancel each other out. In fact, you can find frequencies that can go and cancel other frequencies entirely. This is called destructive interference. To show it to you in the GIF, I have these two waves, one pointing up, one pointing down. When they pass through each other, they disappear for a split second because they cancel each other out. Okay. Now, a very interesting thing happens is if you take a wave, you take a wave and you give someone the fixed end, and you have the wave go, so it bounces off, and you make another wave coming back the other way. But instead of just going randomly, you got a continuously going wave. What can happen, and see, this didn't work right here, is sometimes just some weird shit. This is kind of going crazy. But if you get the frequency just right, instead of looking crazy like this, if the frequency is just right, you get what is called a standing wave. This right here is a GIF of a standing wave being created. What happens is that you have two waves coming. A wave coming to the right that is reflecting and coming to the left. And as the two waves interact, the wave coming to the right and the wave coming back from the left interact, you're going to have a mixture of constructive interference and destructive interference. And what is going to happen is it's going to look like the wave is stationary. It's going to look like it's not moving left or right, but just bouncing up and down in place. Here's a better GIF to show it better. That you can see the waves making it up. The top is the wave moving to the right. The left is the wave traveling to the left. And when they're added up, you get this wave on the bottom. That is a standing wave. And what a standing wave really is two traveling waves moving in either direction. I want to talk about guitars in a little bit. I have a guitar. It's at school, so it's not with me and it doesn't really fit well on the screen. So I bought a very, very, very cheap ukulele for teaching this off Amazon. When you pluck a string on a guitar or ukulele and it bounces off and forth, you're making a standing wave. How you're making a standing wave is when I pluck this string, it causes a traveling wave that moves in either direction down the string to the ends. Once they hit the ends, they reflect and come back. And after I pluck it, these standing waves traveling in either direction, these traveling waves traveling in either direction will form a standing wave, like so. As I said, this happens because there's just waves interfering each other. When you have a standing wave, you normally have what is called nodes and antinodes. Nodes are the areas that don't move or stationary. Antinodes are areas with max displacement. It is of note, standing waves only exist for set frequencies. Like, I obviously didn't get one here. But there will be a very exact frequency that, you know what, this gives me numbers. I should just do the math and figure out exactly what number it is. But there will be a set frequency that if I go and mess around with this enough, will perfectly give me a standing wave. But only for that set frequency. That was close. Those set frequencies, those are called resonant frequencies. We're not going to get into too much detail. That's really close. We're not going to get into too much more detail about that, but just the idea that for set frequencies, you will get these standing waves. Okay. Now, is that a question or? Okay. Let's talk about something else with this guy. When I was just doing the traveling wave, let's go back to loose end. Oh, no end. When I was just doing the traveling wave, one of the things I hit here was the tension in the string. And that when I mess with the tension in the string, I start changing what the wave looks like from low tension to high tension. The reason why is the speed of a traveling wave on a string stretched under some tension will go by this equation. And keep in mind, a standing wave is just traveling waves meeting, which means really the speed of a standing wave can be treated the same way. And the velocity of a wave, which I already said was lambda f, you can still use that, but will be set for a string stretched by f over mu. Well, F is the tension. I'm using F for tension because tension is type of force and not T, because in this chapter, capital T is period. I don't want to have two capital T's in and confuse everyone. Mu is known as the linear density. It is the mass over length. And what that means is if you start messing with the tension in a string, you'll start changing the velocity of the wave. And there's a lot of ways that you can change different things. See, we're talking about waves on a string, right? But when you strum a string, what you're doing is you're causing it to vibrate. It vibrating is going to vibrate the air molecules. Whatever frequency this string is moving at, that'll be the frequency of the sound you hear. We as humans pick up sound frequencies as different pitches. Take, for example, this is a tuning fork. And here's a second tuning fork. This tuning fork, when I hit it, will vibrate at a frequency of 288 hertz. This tuning fork, when I hit it, will vibrate at a frequency of 226 hertz. Sorry if that was loud. That might have been loud. We view frequency as different pitches. And in most instruments, how we actually play them, be it a string instrument like a guitar or ukulele, or even a piano. I don't know if you realize, but a piano is a stringed instrument. Or really any other instrument, any air-based instrument like trumpet, trombone, like anything, or blowing through saxophone, involves us vibrating molecules at a set frequency. And for a string-based instrument, it's just going to be the vibration of that string. So this is harder for me to do with a ukulele and not a guitar because I just don't know ukuleles, how to play them at all. Okay. On a guitar, there's something called harmonics. If you have a traditional guitar, there will be a set of double dots at one spot and then a series of dots on the frets. The ukulele has some too, but they're in different spots. On a guitar's neck, the spot with the double dots, that's exactly halfway on a string. If I take this string and just strum it, what's happening is I am creating waves. And what you see is this wave bouncing up and down. What you see is a wave that has a wavelength of 2L. Because this one string bouncing up and down, this is kind of going like this, is half of a full wavelength. What a harmonic is if you put your finger lightly, not pressing down on the fret, right? But just lightly put your finger there. You can force a node to exist. And once again, a guitar, it's the double dots. A ukulele, I'm pretty sure it is right at the lowest fret because that's the halfway point. And what happens if I put my finger there, I'll force there to be an antinode. You can hear I'm getting a very different frequency without my finger, with my finger. The reason why is what I'm doing is I'm changing the wavelength from 2L to the wavelength to L. I'm cutting the wavelength in half. And because I'm cutting the wavelength in half, well, the velocity of the wave isn't changing. The velocity of the wave is based off the tension in the string, the mass of the string, the length of the string. None of that's changing. See, if I put my finger all the way down, now the length of the string is only going to be from here to here. This part won't vibrate. But if I put my finger there just lightly, not all the way down, both sides are going to vibrate. This side's going to vibrate, and this side's going to vibrate. This side's louder just because of the hole in the guitar or ukulele. And so I'm not changing the length, I'm not changing the mass, I'm not changing the tension, so velocity will not change. But because I'm changing the wavelength, we get a different frequency. We hear a different pitch because we have a different frequency. I mean, this actually gets us into playing a guitar in general, which I got to really get used to saying a ukulele instead. Different strings on a guitar or ukulele have different masses, right? Now, guitars are pretty straightforward. It goes from heaviest string to thinnest string. This ukulele, I don't know if this is normal because the only ukulele I've ever owned, isn't the same. It has the heaviest string is the second one, the thickest string. But on a guitar, the different strings have different thicknesses, right? That if you look at this harp or guitar, probably a guitar, but I don't know why I said harp. You look at this guitar that someone put a camera inside of. Yeah, it's a guitar. That top string is much, much thicker than the bottom string. What happens when you have a string that's much, much thicker is that a thicker string has more mass. And so one of the strings, the thicker string will have more mass. The thinnest string has the smallest mass. This one. And so this guy has more mass than this guy. You hear different frequencies. The reason why, once again, is thicker strings have more mass. If it has more mass, that means mu is bigger. If mu is bigger, that means V is smaller. And if we start changing V, if I go from one value of V to a smaller value of V, and I'm just strumming the entire string, if I'm strumming the entire string, the wavelength isn't changing. And so when I change V, I change frequency. If V goes down, frequency goes down. We view low frequency as low pitch. And so this massive string, the one with more mass, has a low pitch because it has a low frequency. The one that's the lightest one has a higher frequency because it's lighter. Okay. This also gets into how you tune a guitar. When you tune a guitar or ukulele, you play with these pegs up here, right? And then if I start messing with this, if I have this facing away from me, can you still hear the ukulele? Is that coming through the mic? Anyone?
Yeah, it is.
Okay. If I start messing with this, I can really change the frequency a lot. Right? The reason that works, the reason tuning works, and now this is way out of tune, is because you're changing the tension in the string. That when I tone this, I'm putting the string tighter or looser. If you increase the tension, which I have to have this facing me to figure out which way is increasing. Okay, if I increase the, let me go down a bit and make sure I don't snap a string in my face. If I increase the tension, you can hear that frequency going up. It's probably over tightened. The frequency is going up because the tension is going up. If the tension goes up, V goes up. If V goes up, F goes up. Large frequency, higher pitch. Tighter strings are higher notes. Of course, all of this isn't really how you play a guitar. That's just the basis, right? Or a ukulele. You have different strings that make different notes. Yay, out of tune. And you can tune it, which I'm not going to do, by messing with the frequency. But how you actually play an instrument like this is by playing the frets. By instead of just playing a note, putting a finger and pushing down and playing different notes. That actually gets a lot more complicated because what you do when you play a guitar is you start messing with multiple things at once. You see, if I just strum this and I'm not doing a harmonic like I talked about before, what happens is I will always have a wave that has a wavelength of half the length. That the wavelength of the, a wavelength of twice the length. That when I strum this, the wavelength will be twice the length of the string. When you play a guitar and push down on the fret and actually push down to go from here to there, when I do that, what I'm doing is I'm cutting the wavelength, I'm cutting the length of the string in half. I'm going from this length to this length. But I'm also cutting the wavelength in half. I'm going from this wavelength to that wavelength. And so if I play the fret at the halfway point, all the way up here, I'm going to be changing both the length and the wavelength. If I change the length, that's going to change my linear density. That's going to go and make it so that my velocity of the wave changes. And it's going to change by a factor of square root of 2. My frequency, well, when I play this note, my frequency, if I play the note, which is V over lambda, my frequency here, this is frequency half, will be my new velocity over my new wavelength. Well, my velocity changed by a factor of square root of 2, and my wavelength changed by 2. What that means is I changed by a factor of 2 of the square root of 2, which is just the square root of 2. And so this note versus this note has a frequency times the square root of 2 of that note. Because when you play a guitar, when you push down on the frets, you are simultaneously changing the length and the wavelength, changing the velocity of the wave and the wavelength, causing multiple ways to change the frequency. Questions? Yeah, I don't know how to play guitar. I also don't know how to play ukulele. I only have them for this class. Okay. So that is the last bit of this chapter. I do have 10 minutes left that I do plan on using most of this 10 minutes, but that is the end of this material. Because I knew I'd have some time left over, because I always have time left over, I want to talk about the end of the semester. You see, the end of the semester is coming. Today is the 21st. And so, you know what? Do I still have this open? I do. Today is the 21st, and let's go to physical science. Green is you guys. And so next week, we're going to cover chapter 11. The week after, we'll cover chapter 12. And the finals is sometime the week of the 10th. Fun fact, SUNY Delhi hasn't announced the final exam schedule yet. I'm very angry about this fact, like very angry about this fact. I've been sending many angry emails. I don't know when exactly the final is going to be. Sometime the week of the 10th. I wish I could tell you when exactly. I feel bad about that. But that final is coming in a few weeks. So I thought I should give a kind of a setup of what's going to be like. So here's the idea. The final is going to be 9 questions long. You see, your earlier exams were 4 questions, and you had 50 minutes plus 15 minutes to upload. The final will be 9 questions, and you have 2 hours plus 15 minutes to upload. I have posted last semester's final, or if it isn't up, I will post it immediately after class ends. I do plan on going over last semester's final, and I'll do it as a review. When that's going to happen, I'll work out when, once we know when the final is. And the finals breakdown will be as follows. The first 4 questions will be new stuff. The first one will be from chapter 9. The second one will be from chapter 13. The one after will be from chapter 10. And the one after will be from chapter 11. As we go through chapters 10 and 11, I'll give more details, but for 9, it could be any of stress or strain, pressure versus depth, or buoyancy. And for chapter 13, could be springs, could be pendulums, could be both. I normally don't do waves, just because I normally don't. The remaining 5 questions, I said there's going to be 9 questions. You only have to do 4 out of the remaining 5. See, even though the exam is 8 questions long, you only do 8 questions. So it's only 8 questions you have to do. And it's going to be, the remaining 5 questions will be 1 on projectile motion, 1 on F equals ma, 1 on conservation of energy, 1 on conservation of momentum, and 1 about rotational physics. What it is you pick which one you do not want to do, and then you mark down which one you do not want graded. You must mark which one you do not want graded. If you do not mark which one you do not want graded, I pick whichever one you did best on, and I don't count that one because fuck you for making me grade extra problems. Really, the logic isn't me being much of an asshole as I make myself sound to be there. It's really the basis is I don't. If everyone does all the problems and just says, well, I just figure out which one it does, that's a lack of effects on you guys. I want it to be that you acknowledge I don't know what I'm doing here. Not let's just try everything and see what sticks. But oh, I know what I'm doing here. I don't know what I'm doing here. That's why I heavily enforce you must tell me which one you do not want graded. Of note, Vanco Hall doesn't really have a good way to do it 8 out of 9 problems. What it is for the last 5 problems is I'm going to leave a text box visible on the problems. And the one you want to skip, you just write skip in the text box. That's all it is. Vanco Hall grades it real weird. It's going to do some messed up things with the grade. If you look on the actual exam, it'll like mark things in a weird way. That's what I'm getting at here. This is a 250, should be 225. I should fix that. What it is, this is getting into is I figured out how to override that. And so the grade in the grade book will be out of 200 since each problem's worth 25 points, so it's out of 200. Vanco Hall in the actual exam, like when you go into the exam, the grade it gives at the top, that will not necessarily be your correct grade. It'll be the grade I give you in the grade book will be. Any questions about the final? Okay, So I said I'll give more details in the final as we get closer. Like, when is it going to be? That would be a useful detail. But there's the general idea. 9 problems. You must do the first 4, and then you do 4 out of the remaining 5. As I said, so instead of 50 minutes for 4 problems, you have 120 minutes for 8 problems. So you have twice as much time for twice as many problems, plus bonus time. On top of that, I'll give 15 minutes to upload your solutions. Okay? So we'll stop there. See you Friday with practice problems. Have a good day.